Today we are talking about Lewis structures and structural formulas and how to draw them. So let's first discuss what a structural formula is. It's your letters and symbols and bonds to show how the relative positions of the atoms. It's the next step in Lewis dot structures. And the Lewis structure can be used to predict many structural formulas. Okay, so let's talk how you make a Lewis structure. So we're going to talk through all the rules, but then I'm going to draw them so that you can see how they all work together, because sometimes a list of rules without a visual is just a list of rules. So your first step is going to predict the location of certain atoms. Hydrogen is always going to be a terminal atom, meaning on the end, and the central atom is the atom that, as it says here, is the least attraction for shared electrons. Basically, it has the greatest bonding potential. So that's often closest to the left when you're talking about nonmetals. So closest to column 14 or column 14. Then you're going to determine the total number of electrons doing your electron count. And then you're going to, because electrons bond in pairs, you divide your total number of electrons by 2 to get to your bonding pairs. Okay, so let's talk about part 2 of the rules. You're going to place one bonding pair between the central atoms and all of the terminal atoms. You're going to subtract the bonding pairs used, and then as needed, convert to double and triple bonds. But let's really do a couple examples together so we can really see how this works. So let's talk about how to draw and create a Lewis structure and what those rules actually mean, because it's a lot of rules with no visualization. So we were given carbon tetrachloride. So the first thing you're always going to do if you're given words, a word formula, is just to write the formula. So carbon tetrachloride, 1 carbon. Tetra means 4, chlorine. So tetrachloride, 4 chlorines. So CCl4. Okay. Now we're going to go ahead and do the electron count. Okay, and this is how you tell how many electrons you have in your total element. So I have my elements of carbon and chlorine. Okay, carbon has 1 carbon, so I'm going to write 1 next to this. I don't think you can see that color. Let me pick a different color. You have 1 carbon, you have 4 chlorines. Okay. Now, in this element, now you got to think way, way back to valence electrons, and you multiply your amount by valence electrons. So carbon's in column 14, so it's 4 valence electrons. Chlorine is in column 17, so it has 7 valence electrons, and that's per each chlorine. So carbon 1 times 4, so the amount of carbons in this element gives me a total of 4 valence electrons. For chlorine, we have 4 valence electrons per 4, sorry, we have 4 chlorines, and for every 1 chlorine, we have 7 valence electrons. So 4 times 7 gives me 28 valence electrons. Then we add them up for total electrons. 4 plus 28 gives me 32 valence electrons total. So for this entire compound, we have 32 valence electrons to use. But we honestly don't care about total valence electrons. What we actually care about are bonded pairs or electron pairs, because all electrons generally come in pairs. So you divide by 2, so 32 divided by 2 gives me 16 electron pairs. And this is where we start. And another item I'm going to tell you before you start is to draw your Lewis dots. You don't always have to. I always just strongly recommend. So the Lewis dot for carbon is 1, 2, 3, 4, and the Lewis dot for chlorine is 1, 2, 3, 4, 5, 6, 7. And if you're looking at Lewis dots and you're thinking about potential, each lone electron has a bonding potential. So think of it as like ports per bonding. You might move the ports around, but this is what's available. So this chlorine has 1, 2, 3, 4 available for bonding. This carbon, this chlorine has 1, 2, 3. The double electron's a closed port, so it has 3 closed ports, 1 closed port. So for your central atom, that's the one that's going to go in the middle. You're always going to put the element that has the most potential for bonding, so that because then it can hold the most things. So you're going to put carbon there because it's 1, 2, 3, 4 potential for bonding. So you're going to go ahead and put carbon in the middle. Once you put carbon in, you put the chlorine around. Now, you're not going to put 2 chlorine per side. Think of it like, a bonding port. You're going to put one chlorine per side. So I'm going to put 1 chlorine up here, 1 chlorine over here, 1 chlorine down here, and 1 chlorine over here. Okay, now that I have everything set up, the very first thing you do is just put in one bond for everything, because at a minimum, there has to be 1 bond for everything. Okay, once you put those bonds in, you use 1, 2, 3, 4 pairs, because each bond is a pair. You subtract it from here. So now I have 12 pairs left. Okay, and what you're going to do, and I'm going to pull out, is you have to count how many pairs you need to make everything happy, because you can't create a Lewis structure where only carbon's happy but the chlorines aren't. So you kind of have to count. We have 12 pairs, and remember, each one of these chlorine needs 8. That means 2 pairs aside. So this has, 1, 2, 3. This needs 1, 2, 3, and this needs 1, 2, 3, and this needs 1, 2, 3. Okay, so now I can count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I need 12 pairs. I have 12 pairs. So I can go in and make these dots where I have these numbers. So where each number is, you put a pair of dots. And if you're doing this in pen, or pencil, you can go ahead and just erase those numbers. I like to count, and that way I don't have to keep numbers in my head. And you just make them dots so that and you do your count so you can make sure that you're keeping track. And that is your completed Lewis structure of carbon tetrachloride. Okay, so now we're going to do the Lewis structure for carbon disulfide. And I put this in words, so the very first thing you have to do is write the formula. So carbon is the first word. There's no mono because there's mono for the first word. There's no prefix, so there's 1 carbon. Disulfide, 2 sulfurs. So S2. Once you have it written down, you can go ahead and do your electron count. Okay, so we have a carbon and a sulfur. Looking at this element, we have 1 carbon, and because sulfur has that subscript, we have 2 sulfurs. Looking back on the periodic table, the carbon's in column 14, so it has 4 valence electrons. Sulfur is in column 16, so it has 6 valence electrons. So the total amount of valence electrons given by carbon is 1 times 4 is 4 valence electrons. The total amount of valence electrons given by the sulfurs is 2 times 6, because for each 1 sulfur, there are 6 valence electrons, so there's 2 of them, so you multiply it across. So you end up with 12 valence electrons. So we have a total of 4 plus 12, which gives me 16 valence electrons. That's great that we know the total valence electrons, but what we really care about are the pairs. So you divide by 2, and you end up with 8 pairs, or 8 electron pairs. And then we're going to go ahead and put carbon in the middle. And we're going to go ahead and put sulfur on either side. I'd like to do it in a line because it saves paper. It's a lot easier than going it like this. We're going to put sulfur on either side. And the very first thing we're going to do is draw 1 line. Because you always start with 1 line. That's the minimum. So we have 2 lines. So that's 2 pairs used. So now we have 6 pair. Now we're going to do, remember our count. We're going to go ahead and do that in kind of tiny things so we don't get mixed up. So we have 1, 2 here. That's a 1. We have a 1, 2, 3 here. And we have a 1, 2, 3 here. So we need 1, 2, 3, 4, 5, 6, 7, 8. But we only have 6. So this is not going to work. We need to do a double bond. So what we're going to do is do a double bond between this sulfur and this carbon. And that double bond takes the place of both the 1s. And it doesn't matter which numbers you take off. I'm just taking off the same number so you can do it. So we no longer need these, because that double bond replaced both this one and this one, because it's shared by both. So a double bond is a very powerful, that bond that we added takes the place of both. So now we subtract 1 pair, because that's what we just added. So now we have 5 pair to use. But if we're looking at it, we still need, well, let's look. This sulfur has 1, 2, 3, 4 pairs. This carbon has 1, 2, 3, 4 pairs, and this sulfur has 1, 2, 3, 4. But we really only need 1, 2, 3, 4, 5, 6 pair. We only have 5. We can't touch this sulfur because it's already at 8, which means now we have to look at this sulfur. So we add in another line, another bonded pair. That will take the, and I'm just randomly taking ones out. That will take the place of this 2, because one line takes the place of both this one and this one because it's shared between both. So now we say carbon's happy. We use another pair. So now we have 4 pair, and I'm sorry, I didn't do that. And now we only need 1, 2, 3, 4 pairs. We can complete it. So we take our trusty dots, convert what we have left to dots, and no, it doesn't have to be in any particular order. I'm just going over my numbers. If you want to do it a different way, these X's you would either erase or white out to make it the most correct. Any questions on what I've done so far? Okay, so let's do arsenic trichloride. So the first thing you're going to do is go ahead and write the formula. So arsenic is 1 because it's first without a prefix. Tri means 3, so that's 3 chlorine. So it's AsCl3. So once you have that done, you're going to go ahead and do your electron count. Okay, so we put our elements down here. We have As and Cl. We're looking back, we have 1 arsenic and 3 chlorines. We're looking at the periodic table, arsenic's in arsenic's in column 15, which gives it 5 valence electrons. Fluorine is in column 17, which gives it 7 valence electrons. So the total amount of valence electrons provided by arsenic is 1 times 5, because there's 1 arsenic, and for every 1 arsenic, there is 5 valence electrons. The total amount of valence electrons provided by chlorine is 21, because for every 1 chlorine, there's 7 valence electrons, and there's 3. So 3 times 7 is 21. Now you have to add them. 5 plus 21 gives me 26 total valence electrons. But we really don't care about total valence electrons. What we care about is bonding potential. So, or bonding pairs. So we divide it by 2 and we get 13 pairs. Now we have to figure out which one of these will be the central atom. That's the one that goes in the middle. And remember, your central atom's always the one with the largest bonding potential. So you can draw your Lewis structures or Lewis dots. So that's going to be arsenic will have 5 dots, but it'll have 1, 2, 3 ability to bond. And chlorine's going to have like that with 1 ability to bond. So arsenic's going to be your central atom. But arsenic in the middle, then you put chlorine around it. And then you're going to go ahead and you're going to put in your first lines, because you always approach everything with lines. You put in 3 lines, you get to subtract 3, and that gives you 10 pairs left. And now what you always do is you figure out if you can put in the pairs without adding in more lines. So you have 1 here that's needed. You have 1, 2, 3 around here that's needed. You have 1, 2, 3 around here that's needed. And you have 1, 2, 3 around here that's needed. So we can count. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pairs that is needed to make everything full without another bond. We have 10 pairs. We can do that. So we can go ahead and just convert those numbers to dots. And the dots are just like your Lewis dots. It should be in line close to your element, just like we did our Lewis dots. This is just an extension of the Lewis dot. And that is the Lewis structure for arsenic trichloride. Okay, let's do hydroarsenic acid. Well, we know it isn't an oxy acid because of the word hydro. So we should look at arsenic. Arsenic's in the 15th column because of the root arsen. So if it's in the 15th column, it's a charge of 3 minus. So you take that charge number of 3, and that's how many hydrogens you add in front. So it's H3AS. Now that we have that sorted, you have to do your electron count. Okay, we have hydrogen and we have arsenic. Now looking up here, we have 3 hydrogen and 1 arsenic. Hydrogen is in column 1, so it has 1 valence electron. Arsenic is in column 15, and it has 5 valence electrons. So hydrogen, because there's 3 of them, gives 3 valence electrons to the compound hydroarsenic acid. Arsenic, 1 times 5, gives 5 valence electrons for a total of 8 valence electrons. Now, we care about total valence electrons only because we divide by 2 to get electron pairs, and we end up with 4 electron pairs. Now, remember, it's always recommended to draw your Lewis dot. So hydrogen has 1 dot out here. And arsenic has 3 dots and 2 up here. So arsenic's going to be your central atom. Now, hydrogen's always terminal. So that means it's always on the end. And hydrogen is a funny little beastie. Hydrogen will make a covalent bond, but it only wants 1 bond. It doesn't want 8, it only wants 2. So remember when we were talking about like noble gas formation and how hydrogen, because it's in the top row, right next to helium, can only go to 1s2. So remember, hydrogen's happy with 2. So 1 line for hydrogen fills its noble gas configuration rules. So that's why it's always terminal. So that means by default, arsenic has to be in the middle because hydrogen cannot. So we're going to put arsenic in the middle. Now we're going to surround it with hydrogens, and it does not matter where they go. It's just good that we're going to surround them with hydrogens. 1, 2, 3. And now we're going to go ahead and do those first lines because you always have to connect with at least 1 bond. And that's 1, 2, 3 pair. So we're left with 1 pair. And if we go ahead and realize that there's no more for hydrogens, hydrogen's all happy, that 1 pair completes arsenic up here. And now we have everyone happy in the arsenic Lewis dot structure. Okay, so for our final example, we're going to do carbon diselenide. So the first thing we have to do is go from word form to element form. So there's 1 carbon because there's no prefix. And diselenide, that's 2 selenides. So that's Se2. Now that we have our written equation, we can go ahead and do our electron count. Okay, so for your electron count, you have carbon and selenide. These are the 2 ones that we're doing. And then you're going to go ahead and realize you have 1 carbon. It's written 1 time. There's no subscript, so you put 1. Selenide, there's a subscript of 2 and di up there, so you know you have 2 selenides. Then you have to figure out their valence electrons. Carbon is in column 14. That means it has 4 valence electrons. Selenide's in column 16, and that means it has 6 valence electrons. Then you figure out the total amount of electrons provided by each element in the compound. So carbon has 1 times 4 is 4 valence electrons. Selenide is 2 times 6 because for every 1 there's 6, so there's 2 of them. So it ends up being 12 valence electrons. Then you can go ahead and add them together. 4 plus 12 is 16 valence electrons. Now that's the total valence electrons available to make every element into an octet, but we care about bonded pairs or electron pairs. So we're gonna take that 16 divided by 2 and it gives me 8 pairs. Now at this time is when we're gonna go back and draw our Lewis dots. Carbon has 1 dot on each side, selenide or selenium has 6 valence electrons and it already has 2 pairs and only has 2 places really for ports and bonding. Carbon has 4. Carbon has the most potential for bonding, so carbon's going to go ahead and go in the middle. With a selenide on each side. And now that we've drawn those, we're going to go ahead and draw a line between all of them because that's the first thing you do. So you subtract 2 because each line is 1 pair, and we end up again with 6 pairs. Now, the first thing you always do before you assume double or triple bonds is you go ahead and you do your count. So on each empty side, you have to assume that they need 1 more pair. So 1, 2, 1, 2, 3, 1, 2, 3. So I need 1, 2, 3, 4, 5, 6, 7, 8 pairs if I was to not do a double bond. I only have 6, so I can only use what I have, so I have to do a double bond. Well, the first thing we can do is a bond between selenide and carbon, which I'll put in a bond right here. By putting in that bond, I have successfully made this selenide, this one over here. So I'm going to take 2 away over here, and I'm going to take 2 away down here, because I like to match the numbers. That's a me thing. And by doing that, because I basically used 1 bond to take away 2 of the requirements. So I'm going to subtract 1 more pair, because we always keep track of how many pairs we have and how many we've used. So now we have 5 pairs. Okay, and now we're going to count how many we have remaining. We have 1, 2, 3, 4, 5, 6. We have 6 remaining with 5 pairs. So we're going to go ahead and put in another double bond. Well, each selenide, you got to remember way back that we talked about, column 16 can only support 2 bonds. So we have to go to the other side. So we're going to put in 1 more bond between this carbon and this selenide. Okay, so I'm going to go ahead and take away this one and this one, because 1 bond takes away 1 need for each of them. So I'm going to subtract 1 more pair because we just put in another pair. And now we're equal to 4 pairs. And if we look at it, we have 1, 2, 3, 4 left. We can go ahead and convert those numbers to pairs. So I'm going to go ahead and take them out because I want it to be neat. And I'm going to go ahead and draw in my pairs. And that is the Lewis structure for carbon diselenide. The last thing I'm going to do is just remind you of how to look at Lewis dots. So remember, I'm going to do C14 for column 14. That has a Lewis dot that looks something like this. So remember that has 4 valence electrons, but because each side is a single, it has the potential of bonding to 4 things. Remember, for column 15, a Lewis dot looks something like this. So this also shows you your valence electrons. It has 5 valence electrons, but do you see how this one's a pair up here? That means there's no bonding potential if there's a pair. So this one only has 1, 2, 3 bonding potentials. So if you had a column 14 element and a column 15 element in the same compound, column 14 would be your central atom, column 15 would not. Or you might have multiple central atoms depending on the complexity of the compound you're making. We're going to do column 16. The Lewis dot looks something like this. It has 2 open dots or 2 single dots. That means it has a bonding potential of 2, a Lewis valence electron of 6, but these 2 over here are closed, which means this can really only bond to 2 other things or make 1 double bond. This can bond to 3 other things, make a double and a single bond or a triple bond. This can bond to 4 other things, so it can be a triple and a single, 2 doubles, or 4 singles. So there's a lot of these different potentials. Then you have column 17, which is like a Lewis dot that looks something like this. It only has 1 availability bond. That's why column 17 elements are always found on an end, because it doesn't really hold things together. Column 17 elements are never central atoms. So if we're looking at possibility of central atoms, column 14 is your most possible, to column 17 being your least. And then you have hydrogen that only wants 2 electrons, that has a valence, a Lewis structure of this has 1 valence electron, and it is always terminal, and that's the rule. And that is how you do Lewis structures. Thank you. Okay, so let's talk more about Lewis structures today. We've talked about how to draw the Lewis structures, but let's take that next kind of deeper look into the Lewis structure. So when drawing Lewis structures, sometimes you can make more than one arrangement of your bonds or where your electrons are going to go. And when there's more than one valid structure for a molecule or ion, that's called a resonance structure or a resonance. So when you're looking at these examples, you can see that there might be a double bond here, there might be a double bond here, there might be a double bond here or a double bond there. And that's all acceptable placements of that double bond. And therefore, multiple accepted Lewis structures creates resonance. Okay, some other examples of resonance structures are here, where you might have a bond up here, or you're moving that double bond around. Here, you're looking at different placements of that double bond, and that's okay. There's always different examples of how things can be placed. It is called resonance. And then it's important to note that there are exceptions to the octet rule. Sometimes those elements with the odd valence electrons cannot form a fully bonded octet. That's really when we're talking about boron. And then certain compounds with fewer than 8 valence electrons are present, so that's boron. And then hydrogen forms this thing called a coordinate covalent bond. That's when one atom donates a pair of electrons to be shared. Hydrogen creates this coordinate covalent bond because hydrogen does not want 8. Hydrogen wants 2 because hydrogen wants to look like helium. And every now and then a central atom will form more than 8 valence electrons. This is called an expanded octet. And the big element that we look that does that is sulfur. Okay, so here's some examples. So here's examples if we're looking at boron. Boron is happy with 6. And those are covalent bonds, although boron can also form ionic bonds. And then here's hydrogen. Hydrogen's just happy with 2, and it's bonding. And then here's just some more examples of hydrogen bonding. And that is how we wrap up Lewis structures.